Sometimes our system is not at steady state, and we need to solve the mass balance equation for concentration as a function of time. It's a differential equation, so we're going to do some math here. Let's first write our mass balance equation, m dot, which is dCV dt, equals Q times Cn, that's the inflow. I'm going to write the emission term, the source term next, plus E, minus the outflow, Q times C, minus losses due to reactions, first order reactions. So we have minus K times C times V. Now I'm going to divide everything by V, and then I get dC dt equals Q over V times Cn plus E over V minus, now I'm going to factor out the C here, Q over V plus K times C. To make our lives easier, we're going to do a substitution. We're going to group together these terms, which do not have any C's, plain C's in them, and then we're going to group together this term, which is a coefficient in front of the C. So the substitution we're going to make is we're going to call this lowercase script s for source term, and that's going to be Q over V times Cn plus E. And then we're going to have a loss coefficient, script L, which is Q over V plus K. Now I can rewrite my equation as dC dt equals lowercase script L minus L times C. And this will be easier to solve. The way that we solve this is through separation of variables. Followed by integration. So I'm going to divide by s minus LC, multiply by dt. I'm going to get dC over s minus LC to get all the c's on one side and all the t's on the other. And then I'm going to integrate. And I'm going to do an indefinite integral, so I'll get a constant of integration out. On the other hand, I could integrate with limits, but we're going to do it this way with a constant of integration coming out. So I integrate this and I get minus 1 over L, because that's in front of the C, times the natural log of S minus LC is equal to T plus just some constant of integration, which I'm going to call A. Well, now we need to solve for A. I need to set some kind of initial conditions. We're going to say that at time 0, the concentration is equal to C naught. And so now if I make that substitution, at time 0 I have minus 1 over L times the natural log of S minus L C naught is equal to 0 for T plus A. So now I know what A is. In the next step, I'm going to substitute A back in. So now I have minus 1 over L times the natural log of S minus LC, which is equal to T plus this A, which is actually minus 1 over L times the natural log of S minus LC naught. The next step is to solve for C. This is just rearranging algebra. And what I can do is combine my log terms over on one side. So I have minus 1 over L times the natural log of S minus LC over S minus LC naught. So I divided by, or subtracted that the term on the far right-hand side, and then combined the logs. And that is equal to t. So now I can exponentiate both sides, and I have, and also multiply by negative L. So I have S minus LC is over S minus LC naught is equal to e to the minus LT. Then if I keep going here, I can write this as C is equal to 1 over L times S minus e to the minus LT times S minus LC naught. So I multiplied through by the denominator, the S minus LC naught, and then moved the S over from the left-hand side and divided by minus L. And now I can rearrange this as C is equal to S over L minus S over L times e to the minus LT plus C naught e to the minus LT. And now finally I can say that my concentration as a function of time, it's changing, is equal to C naught e to the minus LT, so I'm just switching the order of terms, plus S over L times 1 minus e to the minus LT, where my lowercase script s is q over v times c in plus e, and lowercase script l is q over v plus k, my loss terms. What does this actually look like? We're going to graph it. I'm going to write the equation here again. C of t is equal to C naught e to the minus LT plus S over L times 1 minus e to the minus LT. We're going to break this up into two terms. We'll call them 1 and 2. And then if I graph these, from time 0 to some time out on the x-axis, which I'm going to have be my time, and I have concentration on the y-axis, I'm going to start out at some initial concentration, C naught. And so the first equation is, if I just look at that part, the first part of the equation, the first term, it's just exponential decay. So that's what that looks like. And then part 2, depending on the ratio of S over L, might look something like that. And then I would, so that's 2, the first line I drew was 1, and then if I add them together, I'm going to get something that might look like that. So that's 1 plus 2, starting at some initial concentration and then slowly changing over time and increasing if my source terms are greater than my loss terms. I'm going to show options here of what this curve could look like. So this has my C naught is equal to 1. This is arbitrary units, and I have S and L equal to 1 also. So my first term is shown in blue, and that shows the exponential decay from 1. And my second term is shown in red, and that has an exponential increase, which exactly balances the decrease. So I end up with this flat line shown in purple for the sum of the terms. In this case, I've increased my source term to 10 and left everything else the same. So now you can see, yes, I still have that exponential decay term 1 in blue, starting from 1 and going down, but now my source term 2 greatly outweighs the loss, so I see in red a big increase. And when I add those two together, I get the purple curve, which is an increase in time. And now here I'm showing where the loss term is 10 times the source term, and the coefficients. And so here you can see I've got that exponential decay in blue, and I also have decay I have a slight increase from term 2, but then it kind of hits this maximum, and when I add everything together, I end up with this with less than what I started with, because again, that loss coefficient is greater than the source term.